Now that you've had a sample of the nuts and bolts material that we cover in our boot camp classes, we're ready to give the solution of the problem from lesson number 1. Many of our students have told us that this one Monday morning lesson has cleared up years of confusion and frustration and completely changed the way they had always looked at PLCs. First, a quick review. Here's a PLC 5 system on the left and a SLC 504 system on the right. The programs are identical, and with switch A turned off, both lamps are off. No problems yet. Now, with switch A turned on, both lamps come on, exactly as we expected, and both of the green on the screen displays make perfect sense. This is a nice, friendly little beginner-level exercise, and we've got no problems yet. Next, we added in just one more simple little rung right between the first two rungs. Now, normally, we don't try to control an input device like switch A with the PLC, but as long as switch A stayed off, we still didn't run into any problems yet. Then we turned switch A on. Suddenly we're running into problems that are way past the beginner level. Lamp E still works fine, but lamp F doesn't come on anymore, even though we haven't made any changes to the rung that controls it. And even the green on the screen displays have suddenly quit making sense. The PLC 5 processor on the left treats one XIC as false, even though it's green and looks like it's true. On the other hand, the SLC 504 processor on the right treats one XIC as true, even though it looks like it's false. This isn't trick photography. You can wire up a spare system and try this out for yourself. The point is that the reality of what happens to the lamps cannot be explained the way that many people look at PLCs. This is just one simple example where those old familiar crutches like examines a switch and works like a relay and green means true just cannot get the job done. But now let's go to the whiteboard and see how easy it is for our boot camp approach to clear all of this up step by step. We'll start with both switches turned off, and so both lamps are off. Now suppose that we go to switch A and turn it on. And now let's watch as the processor does step number 1 of the scan cycle and updates the input bits. Do we have current here? Yes. So the processor updates the bit with a 1. Do we have current here? No. So this bit contains a 0. And now the processor does step number 2 of the scan cycle and executes the ladders. This says go look for a 1. Do we have a 1? Yes. So this is true. So this has true coming in. So the processor goes to the bit for lamp E and writes a 1 into the box. Then the processor comes to this, which says go look for a 1. Do we have a 1? No. So this is false, and this has false coming in. And the rule for an OTE says that if false comes in, go write a 0. Don't let this confuse you. It makes no difference that we're addressing an input type bit. The processor doesn't know or care what type of bit he's going to. And when he gets there, he writes a 0 into the box. And here's a common misconception. Notice that switch A out in the field is on, and we do have current flowing in the circuit. But the bit, that's the box, contains a 0, not a 1. Many people assume that the bit status always matches the condition of the switch. That's not always correct. Now back to the scan. This says go look for a 1. Do we have a 1? No. So this is false. Here's another common misconception. Many people explain an XIC instruction by saying that it examines a switch for an on condition. That's not correct. If it actually did work that way, then this condition would be true, because switch A out in the field definitely is on. And back to the scan. This has false coming in, so the processor goes to the bit for lamp F and writes a 0 into the box, which brings us to the end rung. And now it's time for the processor to do step number 3 of the scan cycle and send the output bits to the output module. There's a 1 in this bit, so the processor goes to the module and gives it a signal to turn the output on. There's a 0 in this bit, so the processor goes to the module and gives it a signal to turn this output off. And we're through with this scan cycle. And notice that lamp E is turned on, but lamp F is turned off. At the beginner level of looking at things, the program calls for lamp F to come on whenever switch A is on. But the beginner level won't work here. Lamp F stays off. This result doesn't make any sense when you use the old traditional switching coil analogies that many people believe in, but it makes perfect sense when we follow the step-by-step techniques taught in the PLC boot camp approach. Here's a quick review just touching on the highlights for switch A. We'll start with switch A in the on position. Every time the processor starts a new scan cycle, step number 1 comes around. The processor checks the actual input circuit and finds that we do have current flowing, so he goes to the bit and updates it to a status of 1. Then as the scan continues, this first XIC instruction goes and looks for a 1, and the bit does contain a 1, so this instruction is true. A little later in the scan, this OTE comes into play. We have false logic coming in, and so the OTE goes and writes a 0 to the bit box part way through the scan cycle. You might say that it hijacks the status of the bit. And so by the time the second XIC instruction goes and looks for a 1 in the same box, the bit does not contain a 1, so this condition comes up false. The only thing that makes this problem tricky is that many people firmly believe that the XIC examines the switch, and they totally ignore the status of the bits. This approach often works okay for beginner-level classroom exercises, but there are a lot of troubleshooting problems out there in the real world that cannot be understood using watered-down analogies like this. Now let's talk about these confusing green on the screen indications. Compare the two screenshots and you'll see that a lot of the green seems to be just hit or miss guesswork. When you get right down to it, the green is pretty much like a TV weather forecast. You shouldn't bet the rent on it. Here's the secret. It's not the processor that paints things green on the screen. Instead, it's the RS Logic software that does this. And here's the catch. The software makes a best guess as to what should be shown green on the screen based on information that gets updated from the processor through a communication cable at some particular point in the processor's scan cycle. What that means is that there's a lot that can go on inside the processor that you cannot possibly see on your computer screen. On the SLC 504 screenshot on the right, the pointer shows that the screen status gets updated only after the processor has executed all of the ladder rungs. With a SLC or a micrologic system, that's normally the only time that the RS Logic 500 software gets a chance to talk with the processor. And by that point in each scan, our curveball rung has already written a 0 into the bit for switch A. That's the reason why none of the instructions for switch A are displayed in green, and why bit A is showing up as a 0 on the data table. Don't miss the critical idea that there can be a big difference between what the processor is doing internally and what the RS Logic software is able to show you on your computer screen. Notice in the screenshot for the PLC 520 on the left that the little communicate pointer is at the top of the ladder program, because that's normally when the RS Logic 5 software talks with a PLC 5 processor. And at that point in each scan, our curveball rung has not had a chance to hijack the status of the bit for switch A yet. Specifically, the bit will still have the same 1 status that was stored there during step number 1 of the scan cycle. That's the reason why all of the instructions for switch A are displayed in green, and why bit A is showing up as a 1 on the data table. Actually, the status of bit A is rapidly changing back and forth inside the processor, 1 0 1 0 1 0, but because of the communications timing, the RS Logic 5 software never gets a chance to see a 0, only a 1. Now, let's play hardball. The communications point for a PLC 5 system is slightly more complicated than we just described. Actually, the RS Logic 5 software can communicate with the PLC 5 processor at any point during the ladder execution. We'll cover the details when you go through the class. But for this little preview lesson, we're using a very short program, so the chances are that the communication will take place only at the very top of the scan, like we've shown it here. On the other hand, as your PLC 5 programs get longer, or you use a faster communications link, there'll be more chances for the green on the screen display to make a confusing flicker from time to time. So, summing up, here on this one screen is proof that A, the software cannot show you everything that goes on inside the PLC, B, some of the things that it does show you are wrong, and C, you need the techniques we teach in our PLC bootcamp classes to troubleshoot many types of problems. Many training courses cover only how PLCs are supposed to work. Our bootcamp classes are different because we'll teach you how to deal with PLC control systems when they don't work. Read through the comments on our website and see how this step-by-step approach has helped our former students finally understand PLCs.